The crossbow did not emerge as a modification of the bow in a single moment. It appears in the archaeological record as a distinct mechanical solution. Its defining innovation was not the bow itself, it was the trigger. The earliest confirmed evidence of crossbows comes from ancient China. Archaeological excavations dated to the late spring and autumn period and the early Warring States period, roughly the 5th to 4th centuries BCE, have revealed bronze trigger mechanisms of remarkable sophistication. These mechanisms were not simple hooks. They were multi-component systems, carefully cast in bronze, designed to hold significant tension safely. Excavated examples from sites in Hubei and other regions show standardized parts, a sear, a trigger lever, and a locking mechanism housed within a wooden stock. Although the wooden components rarely survive, the bronze elements endure. Their survival allows precise dating. Their casting techniques reveal advanced metallurgical knowledge. Some trigger assemblies bear inscriptions indicating controlled production and possibly state oversight. The crossbow in early China was therefore not merely a hunting device. It was a mechanical instrument integrated into organized systems. The innovation lay in separating energy storage from muscular endurance. Unlike a handheld bow, which requires the archer to maintain full draw strength, the crossbow allowed energy to be stored mechanically and held indefinitely until release. This shift represents a conceptual change in design. The user no longer needed to sustain tension. The mechanism did. Bronze was particularly suited for this application. It resists deformation. It holds precise edges. It allows repeatable casting. The trigger systems discovered demonstrate tolerances and alignments that suggest careful engineering. This is not an improvised adaptation. It is deliberate design. Archaeological evidence suggests that by the 3rd century BCE, crossbows were widespread in Chinese territories. Standardization becomes visible in tomb finds where multiple similar mechanisms appear together. The presence of bronze components also indicates resource investment. Casting bronze requires infrastructure, molds, alloy control, skilled labor. The crossbow, in this early form, represents mechanical specialization. Meanwhile, in Europe, evidence appears later. Greek and Roman sources describe devices such as the gastrophetes, literally belly bow. This device, referenced in the 4th century BCE, used a stock and a spanning mechanism pressed against the body to draw the string. Unlike the Chinese crossbow, the gastrophetes relied primarily on mechanical leverage rather than an internal bronze trigger assembly of identical design. However, the principle is similar. Energy stored in a bow, mounted on a rigid frame, released by a mechanical action rather than direct finger release. By the Roman period, various forms of mechanical projectile devices existed, including handheld and mounted torsion systems. The European crossbow, as it later became known, appears clearly by the early medieval period. Iron and steel components replace bronze in trigger assemblies. The mechanism evolves but maintains the same core principle, a locking system capable of holding tension safely until controlled release. The archaeological record in Europe is less complete than in China for early periods. Organic materials degrade. Wooden stocks disappear. What survives are metal elements, iron trigger components, bolt heads, occasionally preserved wooden fragments in waterlogged contexts. Dating relies on associated artifacts and stratigraphy. Unlike the Chinese bronze triggers, which provide precise chronological anchors. European early examples are often reconstructed through indirect evidence. The question of independent invention arises naturally. Did the crossbow originate in one region and spread, or was it conceived separately? Most scholars suggest independent development. The mechanical principle, mounting a bow on a stock and adding a trigger, is conceptually accessible once certain material technologies exist. In China, advanced bronze casting and organized military production created the conditions for early mechanized triggers. In the Mediterranean world, experimentation with torsion devices and mechanical leverage suggests parallel innovation. Independent invention does not imply identical design. It implies convergence. When different societies face similar mechanical challenges, similar solutions may emerge. The crossbow represents one such solution. Its novelty lies not in the curved limbs. Those existed for millennia. Its novelty lies in mechanical mediation between stored energy and release. The trigger system transforms the relationship between user and tension. The operator becomes a controller rather than a constant source of force. This shift marks the crossbow as a distinct technological category. Archaeological evidence from China remains the earliest clear material confirmation. Bronze trigger mechanisms dated to approximately 400 BCE stand as physical proof of advanced mechanical thought. European evidence emerges later, but reflects a comparable conceptual framework. Across regions, the crossbow did not replace the traditional bow immediately. It existed alongside it. But from its earliest confirmed origins, the crossbow represented a different approach. Not stronger wood, not greater draw length, but mechanical retention of energy. A small system of moving parts holding tension until a deliberate release. That mechanical difference defines its early history. At first glance, a crossbow appears to be a bow turned sideways, but mechanically, it represents a different system. The traditional bow is a handheld elastic device. Energy is stored when the archer draws the string backward. The limbs bend. Elastic potential energy accumulates in the wood or composite structure, but that energy can only remain stored as long as the archer maintains the draw. The human body is part of the mechanism. Muscles sustain tension. The moment the fingers release the string, the stored energy transfers to the arrow. The bow is therefore a continuous system. Human force to limb deformation to projectile motion. In contrast, the crossbow separates these phases. The bow is mounted horizontally on a rigid stock, often called the tiller. The stock serves as a structural frame. It aligns the bow, stabilizes the projectile, and houses the trigger mechanism. This rigid frame transforms the system from dynamic to static. When the string is drawn back on a crossbow, it is locked into position by a mechanical catch. The user no longer needs to hold the tension manually. The energy remains stored in the bent limbs, but muscular effort is removed from the equation after cocking. This distinction is fundamental. In physics terms, both devices store elastic potential energy. The limbs behave like springs. When bent, they accumulate energy proportional to their deformation and stiffness. That energy is released when the string returns to its resting position. However, in a traditional bow, the draw must be sustained at full tension until the moment of release. In a crossbow, the draw is completed first, then secured. Only later is it released. The mechanical addition that makes this possible is the trigger system. At its simplest, the trigger holds a rotating nut or sear that captures the string. The string rests against this catch under full tension. The trigger acts as a lever. When pressed, it rotates or shifts the catch just enough to free the string. This means that the force required to release the string is small. The trigger does not oppose the full draw weight directly. It manipulates geometry. Through leverage and mechanical advantage, a small finger movement controls a large stored force. The stock plays another critical role. It provides alignment. In a handheld bow, the arrow rests against the archer's hand or a small shelf. In a crossbow, the projectile, typically a bolt, rests in a groove along the top of the stock. This groove stabilizes direction. It reduces lateral deviation. The stock therefore converts the crossbow into a shoulder-fired mechanical system rather than a freehand one. From a construction standpoint, the crossbow combines three main structural elements: the prod, the bow itself; the stock, the rigid frame; the trigger mechanism, the release system. The prod stores energy. The stock stabilizes and aligns. The trigger controls release. Together, they form a compound device. Another difference lies in draw length. Traditional bows typically have longer draw distances. This allows energy to build progressively. Crossbows often have shorter power strokes. To compensate, the limbs may be stiffer. In later European models, steel prods increased stiffness dramatically. Stiffer limbs store more energy over shorter deformation distances, but they require greater force to cock. This is why spanning mechanisms developed: belt hooks, cranks, windlasses. Mechanically, the crossbow shifts effort from momentary muscular endurance to preparatory mechanical work. Instead of holding tension for seconds, the user invests effort in cocking the device once. After that, the system remains under tension independently. This introduces a new characteristic: stored readiness. The crossbow can remain drawn without continuous effort. This changes its operational behavior. In terms of pure physics, both bow and crossbow convert elastic energy into kinetic energy. The efficiency of that conversion depends on limb mass, string mass, and friction. A heavier limb reduces efficiency because some energy accelerates the limb itself rather than the projectile. Shorter power strokes can also limit maximum velocity. Yet mechanical stability can improve consistency. The crossbow therefore trades dynamic fluidity for mechanical control. The handheld bow is responsive. The crossbow is structured. One relies on coordinated body movement. The other relies on engineered components. In construction terms, mounting the bow on a stock fundamentally alters load distribution. The stock must withstand horizontal shear forces. It must resist torsion during release. Its geometry affects accuracy. Wood selection for the stock differs from that of the prod. The prod requires elasticity. The stock requires rigidity. This division of material roles illustrates a more segmented design philosophy. The crossbow is not merely a stronger bow. It is a bow integrated into a mechanical frame. Its defining principle is not increased force, but mechanical mediation between stored energy and release. Where the traditional bow keeps the human body inside the energy loop, the crossbow places a mechanism in between. That separation between effort and release defines its mechanical identity. The defining feature of the crossbow is not the bow itself. It is the trigger. Without a locking and release system, a crossbow would simply be a horizontally mounted bow. The trigger transforms it into a controlled mechanical device It allows energy to be stored safely and released deliberately. In early China, bronze trigger mechanisms represent one of the earliest confirmed examples of complex mechanical engineering in handheld projectile systems. Archaeological finds from the Warring States period, dating to around the 5th to 4th centuries BCE, reveal multi-part bronze assemblies cast with remarkable precision. These mechanisms were not simple hooks. They consisted of several interlocking components: a sear or catch, a rotating nut, a trigger lever, a housing frame. Each piece was cast separately and assembled into a functional unit. The bronze used was strong enough to withstand sustained tension. When the string was drawn back, it rested in a notch within the rotating nut. The nut was prevented from turning by the sear. The sear itself was held in place by the trigger lever. When the trigger was pressed, the lever pivoted, allowing the sear to disengage. The nut rotated. The string was released. This sequence required careful geometry. The contact surfaces had to align precisely. Too shallow, and the string would slip prematurely. Too deep, and the trigger pull would require excessive force. The system demonstrates understanding of mechanical advantage. The trigger does not directly oppose the full draw weight. Instead, it manipulates leverage. A small movement at the trigger results in the release of a much larger stored force. This is engineering through geometry. Bronze casting allowed repeatable shapes. Some surviving examples show standardized forms, suggesting regulated production rather than isolated experimentation. The surfaces that bear tension were often reinforced or thickened. Stress concentration was managed through shape rather than bulk. The trigger housing also protected the mechanism from debris and impact. In Europe, later crossbows developed steel trigger mechanisms. Iron was used earlier, but as metallurgical techniques improved, steel components became common in medieval crossbows. The fundamental principle remained similar: a rotating nut or latch held under tension, secured by a sear, released by a trigger lever. Steel offered greater tensile strength than bronze. This allowed higher draw weights. As steel prods became common in European crossbows, the forces involved increased significantly. The trigger mechanism had to withstand greater stress. Precision became critical. The surfaces of contact were hardened. Edges were shaped carefully to prevent wear. Excessive wear could lead to accidental discharge. Safety became a design priority. Unlike a handheld bow, a cocked crossbow stores energy without human support. If the trigger fails unexpectedly, release is sudden. The mechanism therefore required reliability. Engineers addressed this through several design choices. Deep string notches reduced slip risk. Strong housing walls prevented spreading. Trigger travel was limited to prevent over-rotation. In some designs, secondary safety catches were added. These additional components blocked trigger movement unless deliberately disengaged. This reflects a growing awareness of controlled force management. The trigger mechanism is essentially a controlled gate. It separates stored energy from immediate release. Its engineering must balance two opposing requirements. It must hold under high tension. It must release smoothly with minimal effort. If it holds too tightly, the trigger pull becomes heavy and unpredictable. If it holds too lightly, accidental release becomes possible. The solution lies in angle geometry. The contact surfaces between nut and sear are angled carefully. These angles determine mechanical stability. Small changes in geometry significantly affect performance. In both Chinese bronze and European steel mechanisms, we see deliberate shaping to manage these forces. This is not decorative metalwork. It is functional engineering. The trigger system also isolates the operator from direct tension. In a traditional bow, the fingers feel the full draw weight. In a crossbow, the trigger feels only the reduced force created by leverage. The user experiences control without strain. This shift in force interaction represents a mechanical abstraction. The mechanism mediates between stored energy and human input. It translates small movement into large release. Durability depends on material strength and surface integrity. Repeated firing causes wear at the contact points. Polished surfaces reduce friction. Hardening increases lifespan. Proper maintenance prevents deformation. The trigger mechanism must remain dimensionally stable. Even slight bending or rounding of edges can alter reliability. Thus, the trigger becomes the most technically demanding component of the crossbow. The prod stores energy. The stock supports alignment. But the trigger governs safety and precision. It is the decision point. Energy waits within the bent limbs. The trigger determines when that energy moves. From ancient Chinese bronze castings to medieval European steel assemblies, the core principle remains consistent. A small lever controlling a large force, a contained release, a mechanical boundary between tension and motion. The trigger defines the crossbow not by increasing power, but by engineering control. A crossbow is not a single object. It is an assembly. Each part has a distinct role. Each material is selected for a specific mechanical reason. Unlike the handheld bow, which integrates flexibility and structure into one piece, the crossbow divides function across components. This division defines its construction. The main elements are the stock, tiller, the prod, bow limb, the string, the trigger mechanism. Each relies on different materials. Each serves a different mechanical purpose. The stock, often called the tiller, forms the rigid foundation. It is typically made from hardwood. Oak, walnut, beech, or other dense species were commonly used in Europe. The stock must resist bending. Unlike the prod, it should not flex. Its purpose is alignment and stability. The groove along its top guides the bolt. This groove must be straight. Even minor warping affects trajectory. The stock also houses the trigger mechanism. It must hold metal components securely. Wood chosen for the stock is selected for strength and dimensional stability. Grain direction runs lengthwise. Knots are avoided. Cracks are unacceptable. The stock absorbs recoil forces generated when the string snaps forward. It distributes stress across its length. The prod, the bow itself, performs the opposite role. It must flex. Early crossbows used wooden prods similar to traditional bows. Wood required careful shaping and seasoning. Over time, composite prods appeared. These used layered horn, sinew, and wood, similar to step bows. Later, European crossbows often employed steel prods. Steel increased stiffness dramatically. A steel prod stores energy in elastic deformation of metal. Its advantage lies in strength, but it adds weight. Heavier limbs reduce efficiency. Steel prods require stronger spanning mechanisms. The choice of prod material determines draw weight and energy storage capacity. Wood prods are lighter but limited in maximum force. Composite prods improve elasticity to length ratio. Steel prods increase durability and strength, but demand mechanical assistance for cocking. The string connects the prod tips. It transfers stored energy to the bolt. Historically, strings were made from twisted natural fibers. Hemp, flax, silk, or sinew were common. The string must resist tension without excessive stretch. Too much elasticity reduces efficiency. Too little flexibility increases risk of snapping. The string is both strong and replaceable. It experiences wear from repeated contact with the nut of the trigger mechanism. Regular maintenance was necessary. The trigger mechanism, constructed from bronze or steel, controls release. Its materials must resist deformation under load. Bronze allowed precise casting in ancient China. Steel became dominant in medieval Europe due to improved metallurgical techniques. The trigger assembly consists of a nut or rolling catch, a sear, a trigger lever, a housing. These components must align precisely. If misaligned, release becomes unreliable. The interface between string and nut experiences concentrated stress. Hardening reduces wear. Polishing reduces friction. Beyond these primary parts, additional construction details appear. Bindings secure the prod to the stock. Rope, sinew, or metal brackets hold the bow in place. The joint must withstand shear forces during release. In some designs, metal stirrups are attached to the front of the stock. These assist in spanning. Their integration requires reinforcement of the stock tip. Material selection is not decorative, it is functional. Wood for rigidity, horn for compression resistance, sinew for tensile strength, steel for durability under high stress, fiber for controlled elasticity. Each material responds differently to humidity and temperature. Wood expands and contracts. Steel responds to temperature change, but not moisture. Horn and sinew are sensitive to humidity. Construction must account for environmental exposure. The crossbow reflects a layered philosophy. Rather than relying on one material to perform all functions, it assigns tasks. The stock stabilizes, the prod flexes, the string transfers, the trigger controls. This separation of roles increases complexity, but it also increases specialization. Repair becomes modular. A broken string can be replaced. A worn trigger part can be reforged. A damaged prod can be exchanged. The crossbow, therefore, resembles later mechanical systems more than earlier elastic tools. It is assembled. It integrates woodcraft and metalwork. It requires carpentry, metallurgy, and fiber preparation. Its construction demonstrates coordinated craftsmanship across disciplines. Where the traditional bow is shaped primarily from one material, the crossbow is engineered from several. Its structure reveals intention. Each part exists because the others demand it. The rigidity of the stock makes a trigger possible. The trigger allows stored tension. Stored tension demands stronger materials. Stronger materials demand reinforced joints. The system evolves as a whole. In its construction, the crossbow becomes not merely a curved limb with a string, but a structured assembly in which materials are selected for the specific forces they must endure. The crossbow stores energy before it is fired. But that energy must first be placed into the limbs. Drawing a traditional bow requires the strength of the arms and back. Drawing a crossbow often requires mechanical assistance. As crossbows increased in power, their draw weights exceeded what could comfortably be pulled by hand alone. Spanning methods developed as solutions to this problem. Each method reflects an application of mechanical advantage. Each reduces the force required at any single moment. The simplest method was manual spanning. Early crossbows with moderate draw weights could be cocked by hand. The user placed a foot in a stirrup at the front of the stock. With both hands, the string was pulled backward until it engaged the trigger nut. This required significant strength. The arms and back provided direct force. No leverage beyond body mechanics was involved. Manual spanning limited maximum draw weight. As prods became stronger, especially with the introduction of steel, manual force alone became insufficient. The next solution was the belt hook, a metal hook attached to a belt or harness. The archer would place a foot in the stirrup, then attach the hook to the string. By straightening the legs and leaning backward, the body weight assisted in drawing the string. This method transferred effort from the arms to the legs and torso. It increased effective force without adding mechanical complexity. The belt hook represents a shift toward body lever integration. The body becomes part of a larger lever system. Force is distributed more efficiently. As draw weights continued to increase, dedicated mechanical spanning devices appeared. One of the most recognizable is the goat's foot lever. This hinged lever device attaches temporarily to the crossbow. It uses 2 pivot points. When pulled backward, the lever multiplies force through mechanical advantage. The geometry of the lever reduces required input strength. Short movement at the lever's handle produces longer movement at the string. This reduces perceived effort. The goat's foot is compact and relatively fast. It allows quicker recocking compared to more complex systems. However, its mechanical advantage has limits. Extremely heavy steel prods required even more powerful systems. The most mechanically advanced spanning method was the windlass. The windlass uses a system of pulleys and cranks. 2 cords attached to the string. The user turns a handle connected to drums or rollers. As the drums rotate, the cords wind in gradually. This multiplies force significantly. The trade-off is speed. The windlass requires multiple rotations. Spanning becomes slower, but far easier. The windlass represents a full transition from muscular to mechanical effort. Instead of pulling directly, the operator rotates a crank. Rotational motion converts into linear pull. Gears are not always present, but pulleys and leverage create high mechanical advantage. The final major development is the rack and pinion or cranquin system. This uses a geared mechanism. A small crank rotates a gear. The gear engages a toothed rack attached to the string. As the gear turns, the rack moves backward incrementally. This allows very high draw weights to be spanned with controlled effort. The cranquin demonstrates understanding of gear reduction. Small input torque produces large pulling force. This method allows extreme power, but it is slow and mechanically complex. Across these methods, a pattern emerges. As prod strength increases, spanning becomes less about raw strength and more about mechanical amplification. Each spanning method applies one of the fundamental principles of mechanics: leverage, pulley systems, rotational force conversion, gear reduction. The crossbow's evolution is not only about projectile force, it is about how force is introduced into the system. Spanning determines usability. A crossbow that cannot be drawn is ineffective. Mechanical solutions extend human capacity. They redistribute effort across time. Instead of applying full force in one motion, the windlass spreads effort over many rotations. Instead of arm strength alone, the belt hook uses body weight. Instead of direct pull, the goat's foot multiplies leverage. Each method balances power, speed, and complexity. Manual draw is fast but limited in strength. Belt hook increases force with minimal added equipment. Goat's foot improves leverage with moderate complexity. Windlass and cranaquin maximize power at the cost of speed. These spanning systems reveal an important aspect of crossbow engineering. The prod may store energy. The trigger may release it. But spanning introduces it. Without a method of spanning, the rest of the system remains inactive. Thus, spanning devices are not accessories. They are integral mechanical companions. They transform the crossbow from a strong object into a manageable one. By applying leverage, rotation, and gearing, they allow stored energy to exceed direct human pulling strength. In this way, the crossbow becomes a device shaped not only by release mechanics, but by the methods used to bend it into readiness. The crossbow does not fire arrows in the traditional sense. It fires bolts. At first glance, a bolt appears similar to an arrow. It has a shaft, it has a tip, it has fletching. But its proportions and engineering logic are different. The bolt is designed specifically for the mechanical behavior of the crossbow. Traditional bows use long arrows. The longer shaft accommodates longer draw lengths. It stabilizes through flexing around the bow handle. In contrast, crossbows typically have shorter power strokes. The string travels a shorter distance before releasing the projectile. This allows and requires a shorter shaft. Bolts are compact, often significantly shorter than arrows. Their length corresponds to the groove along the stock. The bolt rests entirely on this groove. It does not rely on finger release. It does not flex around the bow handle. Because of this, bolt spine, its stiffness, plays a different role. In handheld archery, spine must allow controlled flexing. In crossbows, the projectile is already aligned by the stock. Excessive flex is unnecessary and undesirable. Stiffer shafts improve consistency. Mass becomes a defining factor. Crossbows often operate at higher draw weights than handheld bows. The stored energy must be transferred efficiently. If the bolt is too light, excess energy remains in the limbs. This increases vibration. It stresses the prod and string. Heavier bolts absorb more energy. They reduce mechanical shock. They also increase stability in flight. Mass provides momentum. Momentum resists deflection from air resistance. The bolt's center of gravity is usually forward of its midpoint. This forward weighting improves stability. When released, the projectile naturally aligns tip first. Balance determines trajectory consistency. The fletching on bolts is typically shorter and lower profile than on arrows. Because crossbows launch projectiles from a guided groove, less rear stabilization is needed. The groove itself reduces lateral deviation at the moment of release. Short fletching reduces drag. Reduced drag increases speed retention. Engineering choices reflect system integration. The bolt is not designed independently. It is calibrated for the crossbow's energy output. Its mass must match draw weight. Its length must match power stroke. Its stiffness must correspond to the rigid launch system. The tip, often called the head, also differs. Bolt heads are typically heavier relative to shaft length than arrowheads. This reinforces forward balance. Heads may be made of iron or steel. Their geometry influences aerodynamics. Narrow points reduce air resistance. Wider heads increase drag, but alter impact characteristics. Regardless of shape, they contribute significantly to total mass distribution. The shorter shaft changes flight dynamics. Long arrows stabilize through rotational motion induced by fletching. Bolts, being shorter, rely more heavily on forward mass and initial alignment. The crossbow stock ensures a straight launch path. This reduces reliance on flexible correction during early flight. Energy transfer in a crossbow is more abrupt. The string releases quickly. Acceleration is rapid over a short distance. The bolt must withstand this acceleration without bending excessively. This is why rigid construction is preferred. Shaft materials varied historically. Wood remained common. In some contexts, denser hardwoods were selected to increase mass. Heavier bolts are slower, but carry more kinetic energy. Lighter bolts are faster, but may reduce system efficiency. There is a balance between velocity and energy absorption. The crossbow bolt system must be tuned. The bolt protects the mechanism by absorbing force. Too light a projectile increases mechanical strain. Too heavy a projectile reduces effective range. Optimal mass ensures durability and performance. Because crossbows can remain cocked before firing, bolt placement must also ensure stability during waiting periods. The groove holds the bolt in position. Sometimes, clips or retention springs prevent movement. This differs from handheld archery, where the arrow rests lightly against the bow. The bolt is part of a closed mechanical loop. Prod stores energy. String transmits energy. Trigger releases energy. Bolt absorbs and converts energy into motion. Each component depends on the others. The bolt is not merely ammunition. It is a structural participant. Its design reflects the mechanical philosophy of the crossbow itself. Shorter, heavier, stiffer, aligned. Where the arrow complements a dynamic, flexible bow system, the bolt complements a rigid, mechanically mediated one. Its compact form mirrors the compact power stroke. Its mass mirrors the increased draw weight. Its stability reflects the engineered release. In the crossbow, the projectile is not secondary. It completes the engineering system. The crossbow did not remain confined to a single culture. It appeared in different regions at different times, shaped by local materials, manufacturing capabilities, and institutional structures. Its spread reflects adaptation rather than uniform design. In China, the crossbow developed early and achieved high levels of standardization. Archaeological evidence from the Warring States period confirms widespread use by the 4th century BCE. Bronze trigger mechanisms discovered in tombs indicate organized production. Some carry inscriptions, suggesting state oversight or workshop control. The design emphasized mechanical reliability. The prod was often composite. The trigger was bronze. The stock was wooden and straight, with a simple groove to guide the bolt. Over centuries, Chinese crossbows evolved but retained their core architecture. Later innovations included repeating crossbows, in which a magazine system allowed multiple bolts to be loaded sequentially. These devices did not rely on extreme draw weight. Instead, they emphasized repeatable mechanical operation. The crossbow in China became integrated into administrative and military systems. Its production required casting, carpentry, and assembly in coordinated form. Standardization appears in archaeological sets of identical mechanisms. This suggests not isolated craftsmanship, but organized manufacture. In Europe, crossbows emerged later as clearly documented tools. By the early medieval period, crossbows were present across various regions. Unlike the early Chinese bronze triggers, European mechanisms were primarily iron or steel. The prod evolved over time. Wooden prods were common in earlier forms. By the High Middle Ages, steel prods became increasingly widespread. This change altered the crossbow's mechanical profile. Steel allowed higher draw weights. Higher draw weights required mechanical spanning devices. The stock design also developed regional variations. Some were short and compact, others elongated to improve stability. Carving and reinforcement reflect local woodworking traditions. Production in Europe was often organized through guild systems. Craft specialization divided labor between metalworkers and carpenters. The crossbow in Europe became both practical tool and regulated object. In Mediterranean regions, the crossbow adapted to maritime and trade environments. Materials varied according to availability. Humidity influenced construction decisions. Metal components were sometimes protected from corrosion through oiling or surface treatment. The Mediterranean also served as a zone of technological exchange. Ideas moved through trade routes connecting Europe, North Africa, and the Near East. Crossbow designs absorbed influences from multiple directions. Structural similarities appear across regions, but material details differ. Composite prods were present in some Mediterranean contexts. Steel dominated in others. Climate influenced durability. High humidity required careful maintenance. The distribution of crossbows across regions demonstrates convergence around a shared mechanical principle: a rigid stock, a bow mounted transversely, a trigger mechanism holding tension. Beyond that shared structure, variation reflects local context. In China, bronze casting supported early complex triggers. In Europe, improved steel production encouraged stronger prods. In Mediterranean climates, preservation and maintenance shaped design decisions. The crossbow spread did not eliminate traditional bows immediately. Both systems coexisted. The crossbow represented an alternative approach to elastic propulsion. Its diffusion across continents shows that the mechanical logic, store energy mechanically, release it deliberately, resonated in multiple technological traditions. No region adopted an identical form. Instead, each adjusted the system to available resources. Wood species differed, metal quality differed, climate differed, workshop organization differed. Yet the underlying architecture remained recognizable. The crossbow, as it traveled, retained its defining feature: a mechanism separating stored force from immediate human strain. In this way, its regional variations illustrate adaptation rather than reinvention. The design moved across geography, but it bent slightly to match the conditions of each place. The crossbow was not only a mechanical device, it was also a social object. Its structure altered more than energy storage. It altered perception. Unlike the traditional bow, which required years of physical conditioning and practice, the crossbow reduced the barrier between user and stored force. Once spanned, it held tension independently. The trigger required minimal strength. This shift influenced how societies viewed it. Technology that simplifies access to force often generates unease. In some medieval European contexts, the crossbow became associated with accessibility rather than skill. Its mechanical mediation reduced dependence on lifelong training. Where archery reflected cultivated ability, the crossbow represented engineered advantage. The concern was not purely mechanical, it was structural. If a device allows less physically trained individuals to generate significant force, the balance between trained specialists and ordinary individuals shifts. In Europe, one of the most frequently cited examples of regulation is the Second Lateran Council of 1139. The the council issued a prohibition against the use of crossbows in conflicts between Christians. The language reflects moral framing rather than technical critique. The concerns centered on perceived lethality and the social implications of widespread use. It did not ban the device universally, nor did it eliminate its production, but it illustrates that the crossbow had become symbolically charged. The regulation reveals perception. The device was not merely a tool, it was seen as destabilizing. The crossbow's mechanical trigger system removed immediate physical exertion from the moment of release. Energy could be stored in advance. The operator could wait. The separation between preparation and action distinguished it from the handheld bow. This mechanical independence may have contributed to social discomfort. In some regions, ownership and carrying of crossbows was subject to restrictions. Urban regulations occasionally governed who could possess them. Guild systems sometimes controlled manufacture. Metal trigger components required skilled production. Control over workshops implied indirect control over distribution. Regulation does not necessarily indicate rejection. It often indicates normalization. Once a technology becomes widespread, systems of oversight appear. The crossbow's presence in legal texts suggests integration into administrative frameworks. In China, regulation operated differently. Historical records indicate state involvement in production and distribution. Bronze trigger mechanisms bearing inscriptions imply centralized manufacturing. Standardization supports oversight. Where production is organized, distribution can be tracked. Rather than moral prohibition, Chinese regulation appears to have emphasized control and supply management. This reflects administrative structure rather than theological framing. In Mediterranean regions, documentation varies. Trade routes facilitated movement of goods and ideas. Crossbows circulated through commercial exchange. Where trade expands, regulation often follows. Metal components, particularly in maritime climates, required maintenance and inspection. Authorities sometimes monitored weapon transport as part of broader governance. The social perception of the crossbow was shaped by its mechanical features. It stored energy visibly. It held tension silently. It did not require immediate muscular strain at the moment of release. This combination made it distinct. The device blurred the line between trained specialist and occasional operator. It represented applied engineering rather than embodied skill alone. Regulation in this context was not solely about danger. It was about order. Who controls access to mechanically stored force? Who governs production of trigger assemblies? Who authorizes distribution? Technological change often precedes legal adjustment. The crossbows spread across regions prompted different responses. Moral prohibition in one context, administrative oversight in another, guild regulation elsewhere. None of these responses halted its use entirely. Instead, they framed it. They incorporated it into social structure. The crossbow became not just a device of tension and release, but a subject of policy. Its engineering shifted how force could be stored. Its presence shifted how societies thought about access to that force. And in that shift, the crossbow moved beyond mechanics into governance. The crossbow did not disappear suddenly. Its decline was gradual. For a period of several centuries, crossbows and firearms existed side by side. Neither immediately replaced the other. Early firearms were slow to load. Ignition systems were unreliable. Weather could interfere with powder. Metal barrels required careful maintenance. In contrast, the crossbow was mechanically stable. Once spanned, it held tension reliably. It required no powder supply. Its operation was predictable. In the 14th and 15th centuries, both systems coexisted in European regions. Crossbows continued to be manufactured. Spanning mechanisms such as windlasses and crannoquins were refined. Meanwhile, matchlock firearms evolved. The key difference lay not only in projectile force, but in energy source. The crossbow stores elastic energy. The firearm stores chemical energy in gunpowder. Elastic systems are limited by material strength. Steel prods can only bend so far. Wood and composite limbs can only store so much tension before failure. Gunpowder, by contrast, releases energy through combustion. As metallurgy improved, barrels could withstand greater internal pressure. Greater pressure allowed higher projectile velocity. Once ignition systems became more reliable, the mechanical advantages of firearms increased. Another factor was training. Operating a heavy crossbow required familiarity with spanning devices. Mechanical spanning could be slow. Windlass systems, though powerful, were time-consuming. Early firearms were also slow, but improvements in flintlock mechanisms increased rate of fire over time. As production standardized, firearms became easier to issue and maintain within organized systems. The crossbow remained mechanically complex. It required maintenance of strings, triggers, spanning devices, and prods. Steel prods were durable, but heavy. Weight reduced maneuverability. In contrast, firearms increasingly balanced weight and power. The energy density of gunpowder surpassed what elastic limbs could achieve. Over time, the maximum effective range of firearms extended beyond that of crossbows. This shift was incremental. In some regions, crossbows persisted into the 16th century. They were not obsolete overnight, but technological momentum favored combustion-based propulsion. The mechanical philosophy changed. Instead of storing energy in bent limbs, energy was stored in compact powder charges. Instead of spanning through leverage, powder was loaded into a chamber. Instead of a trigger releasing elastic tension, a trigger ignited combustion. The principle of controlled release remained, but the mechanism differed fundamentally. Combustion scales differently from elasticity. Elastic systems depend on material resilience. Combustion depends on chemical reaction. As metalworking advanced, barrel strength increased. This allowed firearms to expand beyond the structural limits of steel prods. Economic factors also influenced the transition. Powder production centralized supply chains. Manufacture of barrels and locks became industrialized in later centuries. Crossbows required integration of woodcraft and metalwork in separate domains. Firearms increasingly consolidated production under metallurgical specialization. By the 17th century, in most of Europe, crossbows had largely retreated from primary use in organized military contexts. However, they did not vanish entirely. In hunting, crossbows remained practical. They were quiet. They did not rely on powder availability. In certain regions of Asia, crossbows continued in parallel with firearms for extended periods. Technological decline is rarely absolute. It is contextual. The crossbow did not fail mechanically. It was surpassed in scalability and energy density. Firearms offered higher projectile velocity, simplified long-term logistics, and improved potential for mass production. The transition reflects a broader technological shift from elastic energy systems to chemical energy systems, from mechanical spanning to combustible propulsion. The crossbow represents the culmination of elastic engineering. The firearm represents the beginning of controlled combustion engineering. As that shift stabilized, the crossbow moved from central instrument to secondary role. It did not collapse, it yielded. The crossbow no longer defines military technology. Its primary role has shifted. Today, it exists in controlled environments, sport, historical study, hunting, and mechanical experimentation. Its identity is no longer strategic, it is technical. In sport, the crossbow is standardized. Competitive target crossbows are designed for precision rather than maximum power. The stock is ergonomically shaped. The trigger is refined for consistency. Modern materials replace traditional ones. Aluminum frames increase rigidity. Carbon fiber reduces weight. Synthetic strings resist humidity. The mechanical principle remains unchanged. Stored elastic energy held by a trigger mechanism. But tolerances are tighter. Triggers are adjustable. Safety systems are integrated. The crossbow in sport is engineered for repeatability. Performance is measured in millimeters. Environmental variables are minimized. The device functions as a precision instrument. Historical reconstruction represents another dimension of modern use. Craftspeople and experimental archaeologists recreate medieval and ancient crossbows using period-appropriate materials. Wooden stocks are carved by hand. Steel prods are forged or laminated. Trigger mechanisms are replicated according to archaeological examples. These reconstructions test historical assumptions. How heavy were medieval draw weights? How durable were bronze trigger assemblies? How effective were spanning devices? By building and operating replicas, researchers transform written descriptions into measurable systems. The crossbow becomes evidence in motion. Hunting versions represent a third branch. Modern hunting crossbows incorporate compound systems. Pulleys and cams increase mechanical efficiency. Let-off systems reduce holding strain. Integrated scopes assist aiming. Despite these advancements, the core architecture persists. A horizontal limb system mounted to a rigid stock, a string under tension, a trigger governing release. Materials have evolved. Traditional wood prods have largely been replaced by fiberglass or composite limbs. Steel cables sometimes replace fiber strings. Trigger housings are precision machined. These improvements increase durability and consistency, but they do not alter the underlying mechanical philosophy. Modern crossbows also incorporate enhanced safety features. Anti-dry fire mechanisms prevent release without a bolt in place. Automatic safeties engage after cocking. Trigger pull weight is regulated. These refinements reflect increased emphasis on controlled operation. The mechanical evolution of the crossbow illustrates continuity through adaptation. The earliest Chinese bronze triggers established the principle of controlled release. Medieval European steel mechanisms increased strength. Modern alloys and composites increased durability and precision, yet the structure remains recognizable. A prod storing energy, a stock aligning motion, a trigger mediating release. Unlike firearms, the crossbow did not transition to chemical propulsion. It remained within the domain of elastic mechanics. Its evolution refined rather than replaced its core principle. In the modern context, the crossbow is rarely seen as a primary weapon of conflict. Instead, It is perceived as a sporting instrument, a subject of craftsmanship, a historical artifact, an engineered mechanism. Its cultural meaning has shifted from strategic to technical. It is studied for its design, appreciated for its mechanical clarity, preserved for its historical continuity. Few devices maintain such structural consistency across millennia. The crossbow's defining innovation, mechanical retention of elastic force, remains intact. From bronze sears to precision machined steel triggers, the idea is constant. A lever controlling tension, a mechanism separating effort from release. As an object today, the crossbow stands less as a symbol of power and more as an example of applied mechanics. It demonstrates how materials can be arranged to store force, to hold it safely, and to release it precisely. In this form, the crossbow is not primarily remembered for its role in conflict. It is understood as an engineered system, a structured assembly of wood, metal, and fiber organized around the management of energy.